Well, you've made it past topic 1 for your first part of AP Calculus, and we are into topic 2. Our title of topic 2 is Derivative Rules, and that doesn't mean like the derivative rules. No, it's going to be rules for derivatives. However, you probably don't know what a derivative is right now, which is okay. Now, it turns out that there are really 3 main components in AP Calculus AB that we cover. We cover limits, and strangely, we're almost done with limits. Now, limits will occur all throughout the entire year. They really are the foundation on what calculus is built upon. But we're not going to be nearly as intensive on them as we were in our first unit. So they'll show up every now and then, maybe once every other lesson, just for a proof, and other than that, you really won't see them too much. However, you'll note that on your independent practice, you will have some sort of limit problem probably every day, because we've got to keep all that fresh. We don't want to lose it by the end of the year. The second part of AP Calculus is derivatives, and we're actually going to focus on derivatives for the entire rest of this first semester. The last part that we're going to cover is integration or integrals, and we'll do that for our second semester. So really only 3 main topics, and it's pretty funny when I ask my students when we're coming up to the AP exam or even after, I'm like, well, what'd you learn this year? And they're like, well, we learned how to do limits and derivatives and integrals, and that's really about it. We learned like 3 things all year long. Yeah, 3 things. We're of course going to dive super in depth into those 3, but that's really about it. So this is our introduction to derivatives. There are various rules we have to follow. We're not even going to use the word derivative today. However, we do need a quick review and slightly new introduction to the concept of secant and tangent lines. You first learn about secants and tangents in geometry, but there's a slight chance you might have forgotten that just maybe from a couple years ago. You also might notice that this is day 13 and the last video was day 9. You're like, whoa, what did I miss on 10, 11, and 12? Nothing. Days 10 and 11 were a review for your exam, and day 12 was the actual exam. So now we're on to day 13, our new topic. Let's get to it. So, your opener should take you a couple minutes. They're asking you to calculate the slope of this line using the given points in 2 different ways. Well, 2 different ways. You might have to be creative there. Then you're going to have to explain, what does that slope actually mean? What's it telling us about the line? And then last but not least, they're going to ask you to write the equation of the line in HK form, and depending on who your teacher was, you might not recognize it by that name, and slope-intercept form. So pause the video, go ahead, try that A, B, and C, and then unpause, and we'll get back to it. Alright, slope-wise, let's go ahead and do the easy way first. And the easy way doesn't actually have any math to it unless you consider counting to be math. We need to remember, of course, that our slope is the change in y divided by the change in x, and the easiest way to find that change is just to look at the graph. So I'm going to look at the graph up here, and let's start with the change in y. Well, how far did we change to get from -5 to 5? I would probably just count this, and you'd see that we changed by, if we start on the left right here, I'm going to call this the starting point, we changed by going up 10, right? We went up 10 on the y-axis, so I know it's going to be 10 divided by, and then we want to look at the change in the x, so we start at -2 and we go over to 3, so start at -2, count over to 3, 1, 2, 3, 4, 5, we went to the right 5, and of course we could reduce this to say 2. However, I liked seeing slope as a fraction a little bit more, so maybe you want to reduce it to like 2 over 1, and that's fine too. Of course, there's nothing wrong with 2. Well, I said 2 different ways, so let's quickly look at a second way. The second way is, of course, using our equation, and sometimes you'll see the equation written as y sub 2 minus y sub 1 over x sub 2 minus x sub 1, and that notation is fine. We should remember it doesn't matter how we label our points. I'm going to start with this same point down here, though, just because it's going to be a little bit different. This is going to be our first no, let's call this our second y value. Let's call this y sub 2, and this is our second x value. I guess I should have started with the top point. This is our first y and our first x, right? Those subscripts are just counting the number, and we put them so that we don't just say y minus y. We need to distinguish which y are we talking about. Well, we're talking about the first y and the second y. That's all our subscripts mean. Just a notation, doesn't actually mean to do any arithmetic. So, y sub 2 is -5, being careful with those parentheses here. Y sub 1 is going to be positive 5 divided by, and we have our x sub 2, which is negative 2, minus our x sub 1, which is 3. And if we do the math, we're going to end up with negative 10 divided by negative 5. And you're like, whoa, it's backwards, but of course 2 negatives divide out to make a positive. Same idea. Nothing scary, it's slope. We should know how to find slope. If not, now you do, and I'm proud of you. So, on to part B. Interpreting the slope in context of the change in x values and the change in y. Well, interpreting slope is actually pretty important because it tells us how a line or how any graph moves. So let's think about, let's just use our reduced slope, and you can extrapolate to the rest if you want. So if we're thinking about 2 over 1, what does that actually mean? Well, you can interpret it in two ways. You can read top to bottom, and you can say, if you change the y value, that's the top, right, by 2, then the x value changes by 1, right? So that's not too bad, right? Let's see what that looks like in terms of a graph. So let's start at this 5 right here, and let's change the y value by, or negative 5. Let's change the y value by 2. Now, when I say change by 2, since this is positive, that automatically implies we're going up. If I had said you change the y value by negative 2, then that would mean we're going down. We'd go down by 2, right? So let's look at maybe both of those and see what it would look like. If we change the y value by 2, it means that I'm going to increase my y value by 2. So I'm going to bring my y, and we'll get rid of this, we'll bring my y up by 2. Well, to stay on the graph, to stay on the blue line, what do we have to do? Well, then the x value changes by 1. And again, if the x is changing by a positive amount, it goes to the right. And we'll notice if we follow those instructions, it keeps us on the graph. Now, could we have done it the other way? I mean, imagine if we'd taken negative 10 divided by negative 5 and reduced it to negative 2 divided by negative 1. Well, then our interpretation might be a little different. If you change the y value by negative 2, then the x value changes by negative 1. Well, if we started a y value of negative 5, right, then we want to change the y value by negative 2, which means go down, and change the x value by negative 1, which means go left, and of course we still end up on our graph. Now, this is actually a weird way to interpret this, even though logically it makes sense top to bottom. Look, this is basically saying we're changing the y value first, and then the x is depending on the change in the y. This would be if the y value is the independent variable, right? It's our input because that's the thing we're controlling. And most of our equations aren't in that form. Most of our equations have the y value as the dependent and the x value as the independent. So generally when you see slope, even though this is weird, and I don't know why we decided on this, but we did. So even though this is weird, usually we read bottom to top for slope. So we would say something like, if the x value, and I'm going to stick with change. I really would suggest you use change instead of increase or decrease, because then you get in trouble in case one of these is a negative, because then if you were to say if the x value decreases by, and you might not want to write this, I'm going to erase it, decreases by negative 1. Well, actually what that really means is if you decrease by a negative, it actually turns this to a positive, and then with wordplay you get into trouble, and then the graders are like, what are you talking about? So I really suggest instead of increase or decrease, I like change. So if the x value changes by 1, then the y value changes by 2. And that would be a pretty common way to read the slope. Sometimes you'll see instead of a change, right, you might even see like a delta x equals 1, a change in x is 1, and the change in y is 2. That's pretty common notation as well, so we don't have to write out that word, right? That's our delta, our triangle symbol, right? Our Greek symbol, and it means change in. So if the x value changes by 1, then you have to change the y value by 2. And then if we go back to the graph, I think it'll work exactly the same. We would take a look at this and say we're going to change, actually let's just pick a random point up here. Let's pick this one. If we change the x value by 1, which because it's positive means move to the right, then to stay on the graph we have to change or increase the y value by 2. Right? So that interpretation of slope, I know I spent a long time on it, is actually really important for what we're doing for the rest of this semester. So I think it's important to spend a little bit of time breaking down that slope. Okay, last but not least, write the equation of the line in both HK form and slope-intercept form. Well, let's start with the one that you think is probably easier, which is slope-intercept. And for this problem, you're not wrong, right? Our slope-intercept form, that's our y equals mx plus b. Well, our y is the dependent variable, right? It's isolated. Our slope we saw is 2 over 1. I'm just going to write it as 2x. And then what is our b? Well, b is the y-intercept. And since we have this graph, the y-intercept's really easy to see. It looks like -1. So 2x plus -1, or just 2x minus 1. Easy peasy. Of course, there is also our HK form, and at first glance, HK form is going to seem a lot more complicated than our mx plus b. However, HK form actually simplifies the line writing process, even though it's longer, right? So our slope again is 2. X minus, we're going to have a gap, and then our k, we're also going to have a gap. Well, why does it simplify the process? Well, if we didn't know the y-intercept, let's say that this line crossed the y-axis at some weird value, and you're like, wait, is that -1.75, -1.6? I don't really know. But if you could pick two really nice points, or even just one really nice point, and you knew the slope, then HK form is way easier than mx plus b, because HK form lets you write the equation of the line as long as you know any point. But mx plus b only lets you write the equation of the line if you know the y-intercept. Now, of course, you could solve for the y-intercept and you could write it there, but that's so much work. Why not just use the equation that allows you to use any point? And I'll take a look at any point right now. Let's take a look at this one right here, right? -2, -5. Well, the h, -2, I guess I could label this, and not a good color, is it? So here's our h, here's our k, still not much better, but that's fine. So we have -2 is the h, and our k is -5. And there's the equation of the line. Of course, we could have done the same thing with a different value, right? We could have also used our, let's use this top one up here. We could have done x minus 3, right, plus +5. And that's fine as well. Now, one last thing to note, I think most people probably would have simplified this equation. You would have said, ooh, two negatives, that's exciting. We could rewrite that as a positive. And ooh, positive and negative, we could rewrite that as a negative. And then that, when you compare it to the point over here, is what gives rise to the shortcut of saying, oh, whatever the x is, you do the opposite. And that's just because when you simplify the original form, you do get the opposite. And then whatever k is, just keep the sign. So again, however you want to write it, that's fine. This is the initial form. I probably would have skipped right to this, or down below, same idea, x minus 3 plus 5. Pick your favorite, but I'm going to tell you that although some of you are going to be stubborn and say, no, I love mx plus b, it's the best thing ever, by the end of this unit, I think you might have changed your mind and you'll switch back to HK form. Now, one last piece on this. The AP exam does not care at all what form you use for your lines. As long as it's a valid form, as long as it creates the line, you can use anything. So if you like mx plus b, go for it. Point slope, go for it. Standard form, you're awesome but crazy. HK form, use it. Whatever you prefer, but I think hopefully by even the end of this lesson, I'll have convinced you of the superiority of HK form, but totally up to you. Okay, now that we know that, let's go a little bit quicker. So, you should be able to work this part on your own. Go ahead again, pause the video, work through this, and I'm going to go ahead and do the same once you unpause. Okay, so we're unpausing here. Calculate the slope between the two given points on the right. Well, we have 2 points here. It might even be just quick enough to count it, right? 1, 2, 3, 4, 5 over 1, 2, 3, 4, 5. Cool. So it looks to me like our slope is 5 over 5, or 1 over 1, or just 1. That's easy. Let's double check. Up 1 over 1, up 1 over 1. Yeah, okay. So our slope definitely looks to be 1. Interpret the slope in context of the change of the x and y values. Well, that tells me, let's see, if you, and I'll do what I said I wouldn't do before, but I'll use increase. If you increase the x value by 1, then the y value increases by 1, right? So, does that work for the graph? Well, it actually doesn't, because if you start at this point and you increase the x value by 1, and then you increase the y value by 1, you get a point that's no longer on your parabola. So that's kind of weird, right? We found the slope between the two, but it doesn't really seem to apply to the parabola. So how would finding the slope between 2 points of a curve that's not a line actually be useful? Well, let's go ahead and break this down a little bit. So we're going to split this graph over to the right into 5 equal sub-intervals, so 5 smaller intervals from -2 to 3. Well, if we think of just looking on the x-axis from -2 over to 3, hopefully you can see those 5 sub-intervals, and I'll zoom in just to make it clear. We have 1, 2, 3, 4, 5 sub-intervals. So what I really mean is take 2 points, the 2 points that bookend each interval, and find their slopes. For example, if we look at this first one, here is a slope of x value of -2. Let's look at the x value of -1. Right? And then we're going to find the slope between. So I'm going to notate this by showing the intervals. So I'm going to go ahead and show the interval from -2 to an x value of -1. Intervals are always written with the x's, with the inputs. And then I'm going to find the slope between. And again, I think the slope is going to be easiest just to count down 1, 2, 3. So that's -3, but then to the right 1. So I think our slope is -3 over 1, or we'll probably just say -3. So we get the idea? Okay, so let's try a few more. You can always work off on your own. So the next sub-interval I'm going to look at goes from -1 to 0. -1 to 0, right? Looking at this interval up here, those are the points that correspond on the graph. This to me looks like it's going down 1 and to the right 1. So our slope is going to be -1. And then we look at a few more. Okay, our next one's going to be from 0 to +1. Okay, so 0 to 1 looks like it's right 1 and up 1, so that's going to be a slope of 1. We look from 1 to 2, and our slope, let's see, from 1 to 2, where is the next point? Oh, it's up here, isn't it? So it's going to be right 1 and up 1, 2, 3. So up 3 and to the right 1. And then last but not least, which color haven't I used? There we go. We're going to look on the interval from 2 to 3. And that's going to give me a slope of right 1 and up 1, 2, 3, 4, 5, and up 5. So a slope of 5. Cool. We found 5 slopes. We basically, and if you wanted to look on the graph in terms of colors, we found the slope of this first part, the slope of the second part, the third part, the fourth part, and of course the fifth part, which continues up here. Okay, so we found 5 different slopes, and all of these are slopes of lines, and none of this graph is a line. It all seems pretty curvy to me. So a weird last question. Let's go ahead and find the average of the 5 slopes that we just found here. Right? We know when we average something, this is the mean. We sum all of them up and then divide by however many numbers are there. So it looks like there's 5 values. So I'm going to go ahead and take each of those, and we have -3 plus -1 plus 1 plus 3 plus 5, and we're going to divide that by 5 values. Let's see, these ones cancel, cancel, cancel. 5 divided by 5 is 1. Well, what did we just find here? Well, is it a coincidence that if we averaged the 5 slopes on this sub-intervals, on 5 sub-intervals, that we got an answer of 1? And that matched the slope that we found of just using the 2 end intervals, of using these 2 points here. Coincidence? I think not. Okay, and here's why. The slope between any 2 points, and I'm going to use for really the rest of this year, but also starting today, instead of a y value, instead of writing a point as x sub 1 and y sub 1, we're just going to use a comma f of a. If you wanted, you could do x comma f of x, but we usually assume x is a variable. When I write it as a, that means it's a specific number. So a comma f of a means an input of a and an output of f of a. Or, of course, that's just fancy speak for an x and a y. But writing it like this actually means you get to use fewer variables. You're just using the variable a, and this f isn't actually a variable. Remember, this f is a set of rules. It says input a, do something to a, and once you've done something to a, you get a new output. So we have a point A comma f of A and a second point B comma f of B on any curve. And it's more common to call graphs curves these days in our mathematical process. So don't get thrown off if I say, look at the curve f of x, right? So any curve is known as the average, we just found an average rate of change on an interval a to b. Okay? So using mathematical notation then, we would say the average rate of change, capital R, lowercase o, capital C is very, very common abbreviation or shortcuts for rate of change. You can totally write that on the AP exam. Everyone will know what you're talking about. The average rate of change on the interval a to b for f of x is given by, and I'm just going to show the formula here. You could say the rate of change is average if you wanted, whatever sounds good to you. I think most people would probably just write the formula, but it would be like this. We'd say y sub 2, which in this case is f of b. Actually, let's use this fraction line. It's probably what it's there for. F of b, which is like my second y value, minus f of a, that's my first y value, divided by b minus a. Now realize this is a different way to write y sub 2 minus y sub 1 over x sub 2 minus x sub 1, but subscripts are so last year in math. We are really predominantly going to be using this function notation for y sub 2 and y sub 1, so I would really suggest you get used to this instead of this. There's nothing wrong with this, it's just a little bit more clunky. So this formula gives us the average rate of change if you take the two endpoints of an interval. And that's exactly what we did up here. We took the two endpoints of an interval, we found their slope. That is the average rate of change. Now, what does the average rate of change actually tell you about a graph? Well, up above we split the graph into 5 subintervals. But if I had split it into 10 or 50 or 1,000,000 subintervals, right? So instead of splitting it into these 5 subintervals down here, what if I asked you to split it into, I don't know, 10, where we did this first subinterval, so to like right here, here's a next subinterval, here's the third subinterval, right? We have 10 points instead of 5 up here. Well, if you'd found 10 slopes and added those up and divided by 10, guess what you would have found as your answer? Oh yeah, you would have gotten 1. If you'd done 50 subintervals or 1,000,000, you would still get 1, right? So if you found the average, regardless of the number of subintervals, the answer would still be 1. And that's actually pretty insane, right? It's kind of cool for a graph. So the fact that our average rate of change is 1 tells us two things about the graph. First, over this interval, the parabola on average moves in an upward or positive direction. Now, look at that subinterval, and I'm just going to go ahead and keep using this green here. The subinterval is just this part of the parabola. And visually, looking at that parabola, right, does it look like it goes up more or down more? Well, at first glance, hopefully you're saying, well, clearly up more. I mean, this is the part of the parabola that's going up, and this is going down. Clearly the up part is bigger. But you might be clever and say, well, doesn't it depend on your point of view? Doesn't it look like it's going down more this way and up more this way? Of course, you might be saying, well, nobody reads graphs like that. And you're right. In terms of a graph, we always assume that the graph is moving from left to right because that's how we read. Yeah. So we are going to assume that this means the graph goes down for a short amount. It goes up for actually the same amount right here, but then it continues on up. So on average, this graph is going more in an upwards direction, more in a positive direction than in a downwards or negative direction. And that's why our average rate of change is a positive value. If it was a negative value, it would mean over that interval, the graph goes down more than it goes up. Okay. Second, the average rate of change allows us to discuss how much the y values change for every one increase in the x direction, right? On average. So on average, the y's are increasing by 1 for every x value increased by 1. Okay, now, one way that we're going to use the average rate of change is to write a secant line through any 2 points on a graph. Now, secant does come from the Latin word secare, which is a very cool word, and it means to cut. It's the verb to cut. So, a secant line cuts through a graph using any two given points on the graph. So again, this would be one point on the parabola, this is another. So we're going to go back to the parabola on the opener, which is again up here, right? And we're going to write the secant line that cuts through these 2 points. And we should probably be comfortable with what those 2 points are. Well, -2 comma f of -2 is going to be this point right here, -2 comma f of -2. Yep. And then our other point is 3 comma f of 3. And see how it's really actually convenient. I didn't even have to know the y value here. We just knew it was f of 3. In this case, f of 3, the output when we input 3 is 6. Okay, so how do we write that secant line? Well, the first thing you need to do, of course, is find the slope. So let's go ahead and write the slope here. My slope is going to be, and we do f of 3, that's y2, right? Minus f of -2, y1, divided by 3 minus -2. And I think f of 3 was 6, and f of -2, I think that's 1, divided by 3 plus 2, 5 divided by 5 is 1. We should probably double check that. Is that the right slope? Yeah, okay, we found a slope of 1 up here. We did everything right. I did it algebraically this time. You could have done it by counting. Nothing too bad. Now, we actually want the equation of the secant line in HK form. I'm just going to go ahead and use the first point in interest of space. So I'll call my secant line S for secant line. Why not? So S of x is going to be equal to the slope, that's 1, times x minus -2 plus f of -2. And you, of course, don't have to write it this way. We probably should actually plug in the numbers here. 1, x plus 2, and f of -2, I think we said was 1 over here, right? So plus 1. Great. Now, you could, of course, use that other point as well. I'm actually going to use both equations just to demonstrate it doesn't matter. So one of my secant equations, the one that I just wrote, is that 1, x plus 2 plus 1. And my other secant would use the other point. S of x equals still the same slope, x minus, remember, opposite of h here, so x minus 3 plus 6. But if I'm going to use both of these equations for this next question, which is asking us to convert the equation to mx plus b, it gets a little confusing that they're both called s of x. So I'm going to actually use subscripts after talking about how they're so last year, and I'm going to use a subscript to call this my first equation, s sub 1 of x, and this is my second equation, s sub 2 of x. Now, to convert to mx plus b, of course, we just distribute, which isn't going to change anything. It's going to be our x plus 2 plus 1, which is x plus 3. And I'll do the same thing over here. Distribute, and we end up with x minus 3 plus 6, which is x plus 3. Adding. Okay. So we end up with x plus 3. I mean, does that line make sense? Well, it's a y-intercept of 3, a slope of 1. So let's look back up here. If I started a y-intercept of 1, 2, 3 and use a slope of 1, do I cut through both of those points? I certainly do, right? So I think that equation is good. We've created a secant line by using 2 points on the graph, and it gives us the equation of a line that passes through those 2 points. Very nice, very exciting. Now, is it easier to write this in mx plus b or hk form? Well, looking at just what they gave us here, I think HK form would be much easier, because HK form just requires us to have a point. However, if you had the graph, I think mx plus b would be really easy, because on the graph you just look at it and say, oh, well, if I just connect these 2 points, right, something like that, clearly it passes through 3, so the equation is 1x plus 3. So up to you at this point, but you are going to get a few where you don't have a graph, and I think you'll find that it's probably easier to do HK form. Again, no real preference one over the other, whatever makes more sense to you, but you also have to factor in some efficiency. Now that we've finished our parabola problem, let's look at a practice problem on our own. So that means, if you wouldn't mind, please pausing the video and try parts A through D down below. Hopefully you've unpaused and you're ready to rock and roll. So they gave us an equation s of x, which is a parabola, x squared, right? It's a polynomial, subset of a polynomial, it's a parabola. And they're saying only think about the equation from an x of 3 to an x of 6. And part A asks us to calculate this cool looking formula here, s of 6 minus s of 3 divided by 6 minus 3. Well, that's just evaluating things, so I think maybe we'll use some colors here, s of 6 and s of 3. Let's see what this looks like. So we'll need a fraction line, and I'm going to do s of 6 all at the same time, and s of 3 immediately following, and then we're going to be dividing by 6 minus 3. So s of 6, we need to evaluate 6 into our parabola, so 1/3 6 squared minus 1, and s of 3, same idea, 1/3 3 squared minus 1. 1/3 of 6 squared minus 1, we need to clean this up, right? 6 squared is 36. 36 divided by 3, I think, is 12. 12 minus the 1 over here is going to get me 11. Okay, and in the denominator, 6 minus 3. Let's do the same thing with the yellow part. 3 squared is 9. I'll keep track over here. 9 divided by 3 is 3. 3 minus 1 is 2. And we're going to end up with, well, let's drop down below. I think we end up with 9 divided by 3, which is 3. Nice. Okay, well, B says, what did you just do in A? What does that actually tell us about the parabola? Well, they gave us an interval. We found the slope of the endpoints, right? This is y sub 2 minus y sub 1 over x sub 2 minus x sub 1, right? So we found the slope of the endpoints, but the way that we describe that slope of the endpoints is using the phrase average rate of change. So we would say something like, on this interval, 3 to 6, the average, which I decided to write backwards, the average rate of change, right, that common abbreviation of s of x, and you could write out what it equals, but let's be efficient here. The average rate of change of s of x is 5. Nope, not 5, that's a 3, is 3, or you could say it's 3 over 1 if you wanted. Okay? And again, if you wanted to further interpret, you don't need to, what that's really telling us is that on our parabola, for every 1 that the x increases, the y increases by 3. It's going up faster than it's going out. So to me, well, either way, you got it from there. So, okay, part C. Write the equation of the secant line passing through s of x on that interval. Well, equation, secant line, we know how to write the equation of a line in HK form. I'm going to go ahead and use y equals because someone already used s of x, so I can't use that as secant here. Rude. Oh wait, I wrote this problem. We are of course going to have our slope, and then we're going to have x minus our a value plus f of a. Well, let's start filling pieces in. We know that the slope is 3. We found that on part A, right? The slope between the endpoints. X and then a comma f of a. Well, you have your choice. You can either use what we did in purple, which is an x value of 6, or what I did in yellow, an x value of 3. I'm going to do the yellow one because it's the last thing I wrote. So let's see, 3, so it's the opposite of 3, so x minus 3. Plus, and then what was f of 3? Or in this case, it probably should be s of a, huh? So what was s of 3? I think we found s of 3 was 2. And we've come up with our equation. That's that. Now, if they had asked you on part C to write this in mx plus b, you could totally do that as well. You could say, okay, we know our m is 3, and we know our b is... Oh, wait. On our parabola that we did earlier, we had a graph, and we could totally see where the y-intercept was. Here we don't see the y-intercept, so it's a little bit trickier, and you can find the y-intercept. There's nothing wrong with it, right? Replace your replace your x with 0, do the math, and you'll find your y-intercept. But why do the extra math when you can just do your HK form? Now, if you really did want to find your mx plus b, just start with your HK form, distribute, and we should be just about there. 3x minus 9 plus 2 is going to be 3x minus 7. Let's double check to make sure all that's right and maybe get a visual of what we were doing. So I have all of this pulled up on Desmos over here. On Desmos, I used g of x because Desmos doesn't like s of x, at least at this point. So g of x equals this function. Now, the reason I used g of x instead of just doing y equals is because down below, I can simplify the math by just typing in g of x, and Desmos will know, oh, that means plug in 6 up here, do all the math, very exciting. So by doing this average rate of change, it's a very quick, efficient way to find that it's 3. Also, using that function notation lets me write points quickly. Here are the two endpoints, right? You can see them over here on our function. It shows us the two endpoints, and we were asked to write a secant line that passed through those. Well, there's two ways in HK form we could do that. We could use the point 3 comma s of 3, right, which is this blue point right here. I'll leave that on. And if you look at the secant line, that's the secant line which passed through that blue point, right? Well, it of course passes through the other point as well, but it uses the blue point to create the equation. If you wanted to use the green point to create the equation, you could. It would just be 6 comma s of 6. And you can see that same thing here. It still cuts through those 2 points on the parabola, right? If I zoom out, you can see a nice line that cuts through, goes all the way down to a y-intercept of -7. So I think we did just fine. Okay, let's go ahead and skip to that next page and see where this crazy adventure's taken us. Going back to geometry, oof, the scariest of all journeys. Well, when you studied circles, you had secant lines and tangent lines. So I'm going to go ahead and draw a nice pretty little circle here, and I'm going to keep it kind of small. Oof, not a great circle. I know there's a circle tool on here, but by the time I remember where it is and how to use it, I could have just freehanded one. So here is our circle. They say first draw a secant line, I'll do that in purple, which passes through my circle. Okay, well, in order to have done that, we would have needed 2 points. We calculate the slope, we write an equation, and bam, you have your secant line. But then it says also draw a tangent line. Now, a tangent line just touches a part of our circle. In particular, it touches 1 point on our circle. Okay, that's not a great definition. We're going to get a better one later on, but here is my tangent line. And notice that it's only passing through 1 point on the circle. Now, what's the difference between a secant and a tangent line? Well, with regards to a circle, a secant line touches 2 points and a tangent line touches 1 point. But that's not really a great definition, so you could have put that there. We're going to get a better definition in just a second. So this better way to think about it is how these lines are created. So a secant line requires 2 points on a graph to be created. And of course we saw that up above, right? In order to create this secant line, you're like, well, we only needed 1 point. Well, you actually needed 2, and the part that needs 2 is actually the slope, right? In order to find the slope of 3, we had to use 2 points, y2 minus y1. If we weren't able to find the slope, then we couldn't have created the secant line. So you're right in that this only required 1 point. That's actually really important later on, but the tricky part is the slope required 2. Okay? So tangent lines only pass through and require 1 point. But that makes a tangent line a lot harder to write the equation of a tangent line because all lines require a slope, and a slope requires 2 points. So if someone was to give you, here's 1 point, I want you to write the tangent line through that 1 point, you're like, well, wait, I need a slope. How do I find the slope? And we're going to do more on that later on. So for now, though, let's look at the graph below. We're going to think of that curvy function as f of x. I'm going to go ahead and label that in red. This is f of x down here. It does all sorts of curvy wavies. Very exciting. And then we have a second line which intersects f of x at 2 different points. Now, the strange part is, this line only qualifies as a tangent line to 1 point on the graph, even though the line touches the graph at 1 point here and 1 point here. Right? So this first one, and I shamelessly stole this graph online, and you know that because I don't like the word got, right? We've got. Why got is like redundant. You just say we have a tangent line at this point. We have got. Try to cut got out in your language. It's a weird, ugly word. So either way, we have a tangent line at this point. We don't have a tangent line down here, but the question is why? Okay, why? Well, thinking about that, you might notice that these two lines are very kind of smooth coming together right here, right? They're almost indistinguishable, but that doesn't happen down here, right? In fact, these ones almost look like maybe they're perpendicular. I think perpendicular would have been a little bit more like this, but we don't have that beautiful coming together of the blue curve and the red curve at this point that we do over here. But how do we put that into words? Well, to understand the idea, we're actually going to take a look at the idea of local linearity. Local linearity. Well, I'm going to pull up a Desmos graph, and we're going to look at two intersection points, one at 0, one at 2. And what I'm going to do is zoom in at each point of intersection, and we're going to try to describe in words what's happening there. Okay, so here's my graph. We can see our two intersection points, one at 0, one at 2. Okay, and let's look at what happens if I zoom in on this point of tangency right here. Well, as I zoom in, you'll notice that there are definitely two lines there, but the two lines essentially become indistinguishable. And in fact, if we get really, really close, and I actually have to go a little farther away, you'll notice that these two lines, right, if I had given you something that looks like this, you'd probably say that these two lines don't even look like they're touching each other. And of course, we call two lines that do that parallel lines. And so as I'm zooming in, they become a little less parallel, but they still look pretty darn parallel. But I can zoom in further, and they become parallel. And in fact, if I had shown you this picture, I bet you wouldn't have even been able to tell that one of these isn't a line. Right? So when I go back home, it's very apparent that one's not a line, the red one's not a line. But as I zoomed in really, really far, we not only saw two parallel lines, we also saw that that curve, that red graph, that looks like a cubic graph here, looked like a line. And that is the idea of local linearity. The idea that on most graphs, and we'll qualify that a little bit later, if you zoom in on any part of that graph for long enough, eventually it looks like a straight line. So going back to the other point of intersection, which is down here, that same thing still happens, right? I'm going to try to zoom in as best as I can here. Maybe zoomed in a little bit far, but that's fine, right? Here's that point of intersection, and it looks like we have two perfectly straight lines intersecting. Okay, so very similar to the other point of intersection, but what's different here? Well, what's different here is that if I zoom in further and further, we still see two lines, but what are these two lines not that the other two were? Well, these two lines aren't parallel. And so you'll notice that if you zoom in on a real point of tangency, which this point is a real point of tangency, that the two graphs appear to be parallel with each other. Okay, so let's keep that in mind and jump back and see if we can do a better job explaining points of tangency. Right? So there are actually two ways to think about it. Okay. Part B is the one we just discussed. A line and a function could be a line, but generally it's some sort of curve that's not a line, are tangent if they appear to be parallel in the vicinity, in the neighborhood, right? Vicinity, yeah, in the neighborhood of the point of intersection. Okay. Well, another way to say that is what makes two lines parallel or two functions parallel is that if they have the same slope. And so our more formal definition, and we're going to improve this definition many, many times, but our more formal definition is A, which tells us that a line is tangent to some function f of x at x equals a if at the point of tangency the line and the function have the same slope. Now this is a really strange concept because in the past we haven't really talked about these curvy functions having a slope, but if we treat them as lines at a single point, then at this point of tangency, zoomed in way too far, at this point of tangency we're going to say that they have the same slope. So right here, really, really close to 6, and I have to zoom in really, really far to see that red graph. It might even be too far, I don't know. Really close to 6, they look parallel. Oof, see how hard it is to find that red graph? Yeah, it's just disappeared. I'm not even sure if I'll be able to find it. Yeah, this is as far as I can zoom. That's really funny. But either way, very, very close to 6, they almost look parallel. Right? Maybe I can zoom in a little bit higher. There we go. So they almost look parallel here. Well, they are always going to almost look parallel until we get right to 6. And what happens right at that instant of 6 is the two graphs are actually perfectly parallel to each other. Now they intersect each other, so they're right on top of each other, but for them to be parallel means they have the same slope, the same rate of change. The y value is changing for the exact same nudge in a direction of the x value. So again, you'll a lot of times hear tangent lines defined as saying at the point of intersection, the line and the function have the same slope. Okay, so let's put this into practice. First thing I'd like you to do is graph f of x equals x squared on your graphing calculator or on Desmos, whatever sounds good. Okay. Write the equation of the secant line that passes through those 2 points. Well, I think very quickly I could probably just do f of 3 minus f of 1 divided by 3 minus 1. F of 3, of course, is 9, minus 1, 3 minus 1. I'm looking at 8 divided by 2, which is 4. But they wanted the equation of the secant line. Well, let's use one of those points. Maybe I'll use that f of 1 point, right? So our secant is going to be 4, the slope, x minus 1 plus f of 1, which was also 1 in this case. That's actually very nice. So maybe I'll use the other one just so we can see the differences so nothing gets too confused. So I'll use 3 comma f of 3, which is 9. Great. There is my equation which passes through. Well, is that right? We should probably make sure that's right before we move on. I've made a bunch of mistakes today and had to re-record various parts. So here we go. We're going to go through. I think this looks fine. Let's hit the home button here. Nice. All right, so we have, I called this one h of x. I was running out of different variables, and we have something like this. Okay, I used 1 comma 1. We could have used 3 comma 3. That's totally fine. But does it look like it is secant here through these 2 points? Yes, it cuts through. It's created by 2 points on this parabola. Nifty. All right, now your goal is to do your best to write the equation of the tangent line, which passes through the point 2 comma f of 2. And this is where things get a little bit trickier. So we should probably demonstrate what that actually means on here, right? So I'm going to go ahead, toss out these points for a second, and we're going to look at the point 2 comma f of 2, or h of 2 on my graph. See that point right there? And let's get rid of that secant line too. Your goal is to write a line that perfectly passes through that point, where when our line comes in, and we'll have to think about maybe what's going to happen, it's going to bounce off this graph and appear to be parallel around this point. In fact, it will be parallel at that point. So I think you might be able to tell that the line is not going to come through on the inside of the graph because it's not going to be able to bounce off the point on the inside. In fact, the line's going to come through and bounce off on the outside. So how do we do this? Well, maybe you'd have the cool idea that if we picked 2 points pretty close together on here, we might be able to find their slope and then write a secant line through 2 points really close together. What do I mean by really close together? Well, let's pick a point close to 2 comma h of 2. How about 2.5 comma h of 2.5? Those are pretty close together. So what happens if I find the slope between those two, right? So our slope then, let's see, how could I write this on Desmos and save myself some time? We'll do it like this. And remember, it doesn't matter the order of the slopes. It doesn't matter if the x is going first or second, whichever x goes first or second. Okay, here's my slope, 4.5. And then let's look at the secant line. Well, our secant line, we're going to use our slope, which was 4.5, and we'll do x minus, let's use the point we know it has to pass through. We don't really care if it passes through this. In fact, we probably don't want it to. We know it has to pass through this point, though, because that's the point we're trying to make tangent. So x minus 2 plus h of 2. And you'll notice, of course, that it passes through 2 points because we used 2 points to create this. But it looks pretty darn good. If I turn off this point, it looks like it's almost bouncing off at that point. So notice I'm going to zoom in right here. Okay, and unfortunately it does pass through 2 points in the parabola, and if it passes through 2 points, that means it's not, at least close to here, that means it's not actually tangent. You'll notice if I zoom in far enough, right, these lines are definitely not parallel because they're crossing each other. In order to be parallel, it needs to stay on really the same side of the graph as we go through. But the only thing we're going to have to change about this tangent line right here, because most of it is correct, the point is correct. It needs to pass through this point, right? That's super important. The only thing that's wrong is the slope. The slope is slightly off. So I'm going to record this slope quickly. That's a slope of 4.5, right? When we used 4.5, we found that by finding the point 2.5 comma h of 2.5, or in this case, it's going to be f of 2.5. Probably should have done that. So that's a pretty decent slope. However, I think we can do better. And to do better, what we're going to do is we're going to find a slope or create a slope using 2 points that are even closer together. So instead of 2.5, what if I use 2.1? I think this is going to bring these points really close together now. Yeah, look at that. If I zoom out, they're almost right on top of each other. That's pretty darn good. So 2 minus, and this is the nice part about using Desmos, or this formula, is we can get even better. This gives us a slope of 4.1. Let's turn that on. I'll turn off this second point, and let's go ahead and zoom out. Look at that. That looks really good. The line comes in, kind of bounces off the point, maybe just above, goes back out. Of course, if we zoom in, you'll notice that, and this is really tough here, but if I zoom far enough, you'll notice that they're still not quite parallel, right? The purple one's on the left side, and then on the other one, the purple's on the right side. So it does cross over our graph. Of course, it crosses through the parabola because we created it using 2 points on the parabola, so I think it probably has to cross 2 points here. But either way, we found a very, very close slope of 4.1, right? So 4.1, we found a slope using the point 2.1 comma f of 2.1. Very, very close there. Well, if that's very close, I bet you could probably guess a perfect slope that would work. But just to drive this point home, let's use a point even closer. Let's use the point 2.001. Okay, can you even tell a difference between those 2 points? Right, the red point is right there. They're so close together, though, that I don't think you really will be able to just visually without zooming in really far. And look at that slope it's telling us. It's telling us the slope is 4.001. Well, again, this is still not a perfect tangent line because we used 2 points that are on the parabola. So this tangent line is going to cut through both of those points. But can you tell the difference? I mean, look at how close that looks. That looks like a really good tangent line. And then you're probably saying, well, really good is silly. Why don't we create a perfect tangent line? Well, how do we do that? I bet you could tell that if our slope went from 4.5 to 4.1 when we were close to 4.0001, you could say that the slope is approaching. Approaching. That sounds like a fancy way to say a limit. Well, you might be right, but we aren't going to use any limit notation for today, so we're just going to avoid that, and we're going to say that it looks like the slope is approaching 4. Okay, if I turn off this point and we take a look at these two right here, you'll notice that this graph, this tangent line comes in, it stays on the right of the red, stays on the right of the red, goes back out, and bounces off of one and only 1 point. This is the tangent line for the graph of our f of x equation, and we know it's tangent because it only was created using 1 point, or 2 infinitely close points if you want. Now, we can read into this tangent line a little bit further, right? This tangent line has a slope of 4, so that actually tells us one thing about our parabola as well, and this is really important. It tells us that right at this point, this red point right here, not only does the tangent line have a slope of 4, the parabola also has a slope of 4. Tangent lines and the function to which they're tangent share the exact same slope at the point of tangency. You need to remember that. That comes up so often. So here we go. Let's go ahead and get our conclusion done, and we'll see what we can do. Okay, our perfect tangent line here was y equals, we had a slope of 4, and then it was x minus 2 plus f of 2. Or actually putting values in for everything, x minus 2, f of 2 in this case I think is 4. This was our tangent line. Now, what we're going to do quickly is I would like you guys to try writing a tangent line that passes through -3 and see what you can do. Once you are comfortable with it, unpause and I'll take you through my steps as well. Then we can finish this off and you can be on with your merry day. Alright, -3. Let's take a peek here. So I'm going to keep pretty much everything up here except I want the point -3 comma f of -3. Let's go back home so we can see our graph. We're going to turn this off. Here's my point way up here. We want a line that's tangent to it. Well, I think probably the easiest way is to just pick a value really, really close to -3. So what's really close to -3? How about -3.001? And same thing, negative 3.001. That point, almost indistinguishable, exciting. We find the slope between those 2 points. So a y value for negative 3, a y value of negative 3.001. Parentheses would probably be good here so we don't lose a negative sign, right? Something like that. And notice they told us if we wrote this equation using the point that we want it to be tangent through, this point right here, that if we used 2 points that are really close to each other, the slope is negative 6.001. Okay, let's check that. That looks pretty darn good. It's not going to be quite perfect, but it's very, very close. There's a second point where it passes through. I bet, though, you could say, well, instead of negative 6.001, I bet that means the slope is probably negative 6. And you're right. That would be our perfect tangent line right here. So again, summarizing that, what our tangent line was, we found a slope of negative 6, y equals negative 6, x minus negative 3 plus f of negative 3, or simplifying slightly, x plus 3, then f of negative 3 is 9, and this is our tangent line. Again, that tells us one other thing about our parabola. It tells us right at an x value of negative 3, the slope on both the tangent line and the parabola is exactly negative 6. So down below, describe your strategy, whatever works best for you, whatever you are trying, and then once you're good for that, you can unpause and move on to the last part. The last part introduces a quick definition, and our definition is the instantaneous rate of change. And remember, we started earlier with the average rate of change, and I'll redefine that down below. But the slope of a tangent line is known as the instantaneous, right? Instantaneous, double tan, instantaneous rate of change. And what that means is at the point of tangency, and I'm going to call that a comma f of a point on the graph, the slope of the tangent line, and a lot of times I'll call my tangent line t of x. I probably should have done that up here. You can call it y. There's no real rule, but I like t of x just because it reminds you it's a tangent line. The slope of the tangent line tells us the slope of the graph of f of x at x equals a, and that's again because our tangent line is parallel to the graph at that point. A lot of calculus deals with finding the instantaneous rate of change, or slope if you don't like instantaneous rate of change, instantaneous slope, at a specific point instead of finding the slope between 2 points. And that should make sense because it's much more useful to know how fast something's changing at a specific time than the average rate between 2 different times, right? If you wanted to say, well, how fast is my money in the stock market changing right now? And someone says, well, on average it's changing here. You're like, no, that's not what I wanted. I wanted to know right now, what is the change in my money? Well, that would be the idea of instantaneous rate of change versus average rate of change. So, quick conclusion. If you're writing the equation of a secant line, which we will not do very often, but it does come up, you would calculate the slope between the 2 points, and as a reminder, that slope finds the average rate of change, right? Our average rate of change, again, is given by f of b minus f of a divided by b minus a. You could do it backwards too if you wanted. F of a minus f of b divided by a minus b, same thing. Right? That is our average rate of change. Okay? And if you wanted to actually write the line, you'd create the line s of x equals m, which is what we found up here, right? Our average rate of change. Okay? And then we'd use either one of the points. So you could either use a comma f of a, or you could use b comma f of b. Your choice, doesn't matter. At this point, to write the equation of a tangent line, we would approximate the slope using the desired point of tangency. There's just one point involved in this. For now, the way that we're actually going to find the slope, though, is by choosing a point really, really close to a comma f of a, maybe a 0.001 or something like that, and you're going to find the slope. Then you might want to round the slope to its closest value. For now, we're just going to use really nice numbers. But this slope is going to find the instantaneous rate of change. And then we just write the line t of x equals all of this, where this is our instantaneous rate of change. And then we have, of course, our point A comma f of a. So, long story short, maybe too late. Two things to cover today, secants and tangents. Secants, we have a really set, concrete way of finding it. Tangents, we're really just estimating at this point, and what we're going to learn is that instead of estimating and doing these weird slope things, we are going to have a faster way, and that is one of the beauties of calculus. You should have your independent practice packet for topic 2. I actually included all the dates this year. Next year you might not be so lucky, so you may want to fill in those dates. Don't forget you do have independent practice tonight, and you might want to expect a knowledge check next class. Good luck, and thank you for tuning in.